Okay, today's speaker is Pérez. He got his degree from the University of Barcelona 10 years ago, and then he started collaborating with Miguel Rubí, and then immediately he moved to Belgium to the Catholic University of Leuven, where he got his PhD under the supervision of the CGA project. Then he spent a couple of years in Oxford at the Center for Rudolf Weil Center for Theoretical Physics. Then he went to La Sapienza in Roma, and finally to the King's College London, Department of Mathematics, where he's right now as a junior lecturer since a couple of years ago. His interests are mostly in the area of spin glasses, neural networks, metabolic networks, quantum integrability, random matrices. I've been talking with some of you in the last days, and he will still be here today after the seminar. Okay, so you want to talk to him, you have to do it today. Okay, the title is the spectral density problem graphs with topological constraints.
Okay, thank you very much. Is the camera already actually? Yeah. Okay. First of all, I would like to thank you for inviting me to give this talk here. So the work I'm going to talk today about is a work I started together with my PhD student Tim Rogers, also with some other guys in our group in mathematics, with a collaborator from Japan, Kojo Takeda, and with a person that perhaps some of you know, Pérez, presented from a University of Barcelona. And the idea actually is actually very simple. So you give me an ensemble of random matrices, sparse random matrices, and what I would like to do is to calculate the spectral density exactly. Right? This is what so before going into that, to tell you how to do that, so let me first give you an introduction about, in a nutshell, about the area. So the outline of this talk is going to be full. So first of all, I'm going to give an introduction about the areas in 5 minutes about random matrix theory, some quantitative things like spectral density, etc. Then I will go into details of what we want to do in this talk, which is to try to understand or to calculate the spectral density for a particular case of ensemble of matrices, of random graphs. I will discuss about what I call here asymptotic graph statistics. And then we'll discuss about a general way to calculate the spectral densities of random graphs for a physicist. That essentially what you do is you recast the problem of calculating the spectral density, and you understand that problem as a problem of interacting particles on a graph. Right? Once you have a problem of interacting particles on a graph with temperature 1, you can use usual techniques you use in the area of piezo resistance, like for instance, replica theory or calculating method to try to calculate the spectral density exactly. Then what? We particularize that case to calculate the spectral density for spectral graphs with again particular structure, and then compare analytical results with numerics. I mean, just doing exact numerical generalization, and we'll I conclude some conclusions and future work. Okay. So let me give you in a nutshell what this idea. So the idea is, one of the central problems in a random matrix theory is simply the determination of the mean spectral density of an ensemble of random matrices. Okay? And here you have a various situation. So you have very well-known cases, like for instance, universal laws. For instance, if I give you an ensemble of matrices whose entries are just Gaussian, random variables with a Gaussian distribution, you know that the spectral density is given by the Wigner law. If you have a presence of variant matrices, the spectral density is given by the Marcinko-Pastor law, etc. But as soon as you take a random matrix and you start putting zeros, and the number of zeros you put in the matrix is extensive, it grows with the size of the matrix, then things become a bit more complicated. And it was not until recently that it was found a way to calculate the spectral density exactly, somehow, to a certain degree. This is a work we did recently with my PhD student and collaborators, also a colleague of mine from King's College, and also it was done previously by John Dean. Why this thing is interesting is, like, for me, it's just from a mathematical point of view, it was because it wasn't known how to do it. So it was what I found it interesting, but coming from the area of complex networks, why to know to characterize the spectral density of a sparse matrix exactly is because you can use sparse matrices, random matrices, to model real-world complex networks to a certain degree, right? And this can be bioinformatics, finance, biophysics, metabolic networks, etc. From an analytical point of view, coming from my area, more or less all studies of ensembles of random matrices have been reduced essentially to discussing graphs where the degrees of the vertices are uncorrelated. And an example of that, for instance, is the Erdős-Rényi graph, or random polar graph, or even SL3 networks with progressions, etc. Unfortunately, these are not statistic models to try to model actually real-world complex networks, because one case is that in real-world complex networks you can have communities which are not taken into account in these very simple cases analytically, or you can have complicated correlations between nodes. So the main goal of this work we did is try to find a way to calculate the spectral density for ensembles where you have clustering properties, or you can have correlation between degree correlations as generally as possible. Okay. And then, in order to do the calculation, the way we are going to do it is the following. I will explain the way we do it in this work, maybe another ways. We're going to introduce the degree correlations by what we call here in this paper by hierarchically constrained topologies that I will explain in a second what this means. Do you have some questions about the main goal of the...
Yes.
Go.
I understand in which way the random matrices are related to these problems of complex networks with communities. And what I don't understand is how what you call the central problem helps
I said
helps in doing the sort of things that we do with networks, with communities and that.
well, it's not that perhaps of flavor. So when my idea is like when you tackle a problem, if you can do things as exactly as possible, the best, right? So when you're trying to analyze properties, like for instance, dynamical properties of a complex network, essentially those dynamical properties can be summarized of computing, of understanding the spectral properties of the Laplacian in a given graph, right? They're analyzing the Laplacian on a complex network, and for the analyzing the connectivity matrix is essentially the same problem. So if you know how to solve one thing exactly, you know how to solve the other, okay? So from a mathematical point of view, I would like to know how to solve that problem exactly. So I don't have to rely only on numerical simulations. I can say something, beyond numerical simulations. Something like that. More questions?
I have no idea about random matrices. Can you give in a sentence an example of how you use that in finance?
In finance? Yeah, for instance, in finance, when yes, there's an example. It's not my area again. For instance, in finance, when you the correlations between different assets, the way they are calculated in a market, this correlation matrix can be modeled as a random matrix with certain properties, and then you can compare that correlation with the experiments or just measures in the market. And normally there's a big algorithm, for instance, from Busho or people like this. For essentially what they do is they use random matrices which are covariance matrices to characterize the correlations between different shares in a market. I can give you some. Go ahead.
But this case is not sparse. Because you have correlation for every pair of nodes. Right?
Yeah, that case is not sparse, but the matrix is used to construct the covariance matrix can be sparse.
The matrix you used to give?
So for instance, one way that we did in the first paper is the following. So you can define a matrix Cij like 1 over n sum over mu 1 to p, another matrix xi mu I xi mu j. Yeah. So regardless, you are talking about this matrix of this matrix. For instance, in one we did in the first paper is to consider matrices a sparse matrix where this part is sparse tree-like, and actually this is a sparse tree-like. This is sparse clique-like. But we can discuss this thing later on. Yeah? More questions? Okay, so let's carry on. So let me give you some definitions about the way we tackle the problem. So what is a graph? A graph is just a set of vertices and edges, and the idea is you have set V, and then which is a set of vertices, the set E, which is a set of edges. And from a mathematical point of view, so the edge is encoding the so-called connectivity matrix, and for this talk, I'm going to consider that the connectivity matrix is symmetric. We have a previous paper where we do non-emission case, which is also possible to do. And the connectivity matrix is telling you that if you have two nodes ij, two nodes are connected, if Cij is equal to 1, the other connected Cij is equal to 0. Yeah? And then we find the so-called the nth generalized degree of a vertex I in this way recursively. And what this thing means is the following. So by definition, the zeroth generalized degree is just 1 for the vertices I. And then if you look at this formula, then the generalized degree, the first generalized degree is simply the normal degree of a given vertex, right? So if I calculate using that formula, Ki1 is given by the sum j from 1 to n of Cij, which is just the degree of vertex I, which is normally denoted as Ki, is what the notation I'm going to use throughout this talk. For this is the number of neighbors a node I has. If you go and look at the formula of Ki2, this is equal to the sum j from 1 to n Cij Kj1. This is the number of neighbors. It's the number of neighbors. So you have a neighbor here, side I, is the number of neighbors the neighbors of I have, the total number of neighbors. So for instance, if this guy, so let's put something like this. So this is node I has 4 neighbors, right? So K1 is equal to 4. And then what is K2 for I? So it would be, you sum the neighbors, the number of neighbors of the neighbors of I. So in this case it would be 8. So K2 of I is 8. And you keep doing that. This is also equivalent, so the KL is actually the number of walks that you can do from I. The number of, yeah?
It's the number of paths you can take, not the number of neighbors, because you can't neighbors that.
Yeah, but it has the 2 meanings, as I just said. You can also understand it as the number of walks you can do from I. Yes? Yeah. Very good. So we are going to use this definition to introduce correlations in Ensemble in the following way. So we define our graph ensemble, so this is the ensemble of graphs, as the weight in this form. So that means the following. So we have the probability that 2 nodes ij are connected is given by this way. The probability that 2 nodes are not connected is given by just the opposite way. And then what you do is the following. So you take, you put this Kronecker delta, you constrain these generalized degrees to a given values ki. So here your 3 parameters, if you allow me to say that, so it's just you have q, which is just must be a positive symmetric function that controls the weight for 2 nodes to be connected. And then you have these constraints ki that constrain the value of the generalized degrees.
What is Q?
Q is just a function that controls the weight for 2 nodes to be connected. It's a general function. And this Q, arbitrary function. And this Q depends on the generalized degree Ki and Kj of the 2 nodes connected. Yeah? If you like this kind of preferential attachment weight for 2 nodes to be connected.
And the last delta?
This delta here,
No, the last one.
this one.
I don't see that. So
This Kronecker delta Cij.
No, the other one.
This one.
Okay.
This one is because you want to impose a graph with this hierarchical structure for the generalized degrees. So here I'm imposing that KIC is given. Here I'm using just for a matter of that the alphabet is finite, the same name, but this KI is just an arbitrary value. I want my K, this KI, vector KI to be equal to KIC that you are giving to it. Like for instance in this example, so K1, K1I is before for this particular node, then K2 for this one is 8, etc.
So I'm trying to find out this graph ensemble depends on Q and depends on K.
Yes.
These are parameters of the function.
Yes. And with these parameters, I'm going to use these parameters. Well, in principle, the idea would be to use these parameters to create correlations in the ensemble. The correlations.
So it depends on a particular graph, depends on the given function Q, and the K.
Yes. Right? Now, the first thing to do to try to understand the whole ensemble before going to tackle the problem of the spectral density is to try to understand whether indeed this an ensemble like this one has degree correlations, how general they are. So the first thing we're going to do is to try to understand the graph statistics, and this is done in the usual way using generating functions, things like that. So I'm not going to give the details of the whole calculation, so just let me take you through the calculation, highlighting few parts which actually are going to be important later on. So in the end, everything is going to be boiled down. Actually, for the calculation of the spectral density, will depend only on this joint distribution. So, which is the joint distribution of having a node of node I of generalized degree K. Well, it's the joint distribution of having a node I connected to a neighborhood, right? And the node I has to have this generalized degree K, and the neighborhood has to have generalized degree Q1 to Qk. And you'll see that the spectral density in the end will be just given only in terms of this function. And the point is the following. So for a given for our graph ensemble, what is the value of this guy? Well, indeed, actually, well, this is something just trivial that it correlates, or actually you have a non-trivial correlations. Before going that, of course, there will be other quantities, but that will be given will depend on the marginals of this joint distribution. For instance, if you marginalize with respect to the qk's, you obtain this capital P of k. And this capital P of k is the usual generalization of the probability of finding a vertex connected to a vertex with generalized degree k. Yeah. So if you have a vertex, so suppose that you have a vertex. Now in the simple case where you don't have generalized degrees, if you have a vertex with a degree k, what is the probability of finding a node connected to that vertex of degree k? So that actually, if P is if a small p of k is the degree distribution, if a small p of k is the degree distribution, the probability of finding a vertex connected to that vertex of degree k must be proportional to small k times k, right? And then you normalize this thing by the arch connectivity, and this would be the capital P of k. And in this particular case, when you have generalized degrees, that's the generalization. Right? Questions? Clear? Okay, now how do you calculate the general expression for this joint distribution? By usual techniques of constructing generating function, using saddle point method, etc. So let me just give you briefly the details. So idea is the following. So actually, if we go back, so essentially here what we have to calculate is the average on the ensemble of this product of connectivity entries for the connectivity matrix. Yeah. How do you do that? So you introduce the generating function, you do the trace over this weight, you put the exponential of generating fields, you do the calculation, and then this correlation for the entries of the connectivity matrix are given by the derivatives with respect to this generating field. This generating function for the generating field equal to 0. Clear? It's the usual techniques. Where here you have to put the normalization factor. Cn is just Cn at 0 generating field. So the main problem to this calculation is the obstacle that you have those Kronecker deltas that constrain the generalized degrees to have a given value ki. But this is not an obstacle in the usual techniques. The only thing you have to do is you put a Fourier representation for the Kronecker deltas. So in the end, what you want to have a very nice expression with exponentials, because at the end you want to do the saddle point method. You introduce this representation for the Kronecker deltas, and actually if you look here, at some point you have to do this for each node I. So at some point you have here also a sum for I. So you see here that sites or nodes are correlated in the calculation. So the way to proceed is you want to decorrelate nodes by introducing some order parameter. This is the usual stuff. You would do that by introducing this order parameter, and you also have to introduce this indicator function. This indicator function is the function that forces the generalized degrees to have this dependence. So at the end of the day, actually, so everything boils down to the usual exponential measure, where you have this action, if you want to call it, which is given by this function, right? And here you have the usual beautiful exponential of n. The only thing you have to do is to apply Sistemas descent method, and essentially you're done, right? So
what do we call it for the parameters? This 5?
Just by I have the following philosophy. Whichever I use, whichever mathematical object I need in a calculation of this sort, that I have to introduce to decouple sites by coupling something else. Like for instance, the parameter, or in case you're doing a replica calculation, what you do is actually you decouple sites by coupling replicas. I call by default this thing or the parameter, but it doesn't have to have the physical minimum for the parameter.
So I mean, if you consider the IC model is basically the magnetization.
Yes, but this is not another parameter that has to. It doesn't have to have the minimum for the parameter that it is 0 in one place, different from 0 from other. So
So why does it depend on K and Q at the same time?
It depends on K and Q because let me go back. Well, we can see it from here. Perhaps I can explain you in the test. When you put this measure with these constraints, you have to introduce another parameter that, well, for a given value of K and Q, that will depend on this parameter here, and also a parameter, which appears here, I think. Yeah. So it has dependence on two generalized degrees.
That's what I'm getting lost. Because this correlation function, the correlations, go back.
Yep.
The correlations, these are numbers, which are given by your metrics. Okay.
Yes.
Ensemble metrics, these are numbers. Now, all your definitions, you have these functions Q, K, C. What happened to them? Go back. And you go back.
Yes. Yeah.
You have C, you have a constant C, you have a constant K, you have a.
That's a very good point. Yes. So here, you're wondering why this bracket that means to do the.
No, I wonder what happened with the C, small C that you have here.
Here.
With the big Q you have defined before.
Yeah. So what happens is the following.
So the vector K, which is given there.
Yes. So that's a good point. So what happens here is the following. So essentially, you want to calculate this object. So you have to calculate the bracket. That's the arch over the ensemble, and the matrix C will appear here, 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 but also here. Yeah. But again, I'm telling you that the only thing I have to do is to calculate this object. And the reason for that is that in the way the ensemble is defined, so these constraints, force these values here to take the value kj1. So the dependence on the connectivity matrix here disappears. I can pull in this bracket up to here, and the only thing I have to worry about is to calculate the average over the ensemble of this correlation. But that's because the ensemble, the way I choose it. That doesn't mean that you have other ensemble, you have to do it a bit differently. It will be a bit more difficult. But that's a good problem. More questions? So, well, at the end of the day, this measure, so this correlation for the index of the connectivity matrix would be given by an effective measure, which is given by this formula. And this formula, again, it has this beautiful n, which is just the size of the matrix. So what you do is you do the thermodynamic limit, and you can evaluate this integral using the Stevens method. And what you can do is you can write down the cyclone equations for this function here, and the cyclone equations are given by this. I wanted to write this thing down because I wanted to show you how horrible they are, and that the fact that I'm not going to use them at all. Because now the trick is going to be the following. So because in the end I'm just worried about the spectral density for general complex network with having calculations. So it is the following. So now we have these cyclone equations, which may be in general quite horrible. And then this joint distribution depends on these parameters that appear in the cyclone equations. So if you, for a given parameters in my ensemble, what I should do is to solve somehow the cyclone equations, and once they are solved, I put them here, and I calculate this. I have this joint distribution. Now the point, like for the general case, this is very, very difficult. It's actually horrible to do. But what I'm going to do is the following. Now I understand how this statistics of the graph is related to these ordered parameters, and this relationship is going to appear in my calculation for the spectral density. Okay? And this is everything I need. So I need that this actually, whichever ensemble of graphs I have, is going to give me a joint distribution. Then what I can think is differently. I can think, okay, I'm going to forget about the parameters I'm using to achieve this joint distribution. I assume that I have this joint distribution, and I proceed. Right? So I'm going to forget about this function, Q, parameters, etc. I focus on this joint distribution, and then I try to relate the spectral density to this joint distribution. Right? With the only proviso that the type of ensembles I'm studying are ensembles which are tree-like, are sparse graphs. That's the only proviso I have to be careful about. Right? So this is very important because I can overcome a problem which was actually not noticed in previous works, where in principle these cyclone equations are difficult to solve, and then people what they do is try to particularize, to study very specific cases, like for instance having just 1 generalized degrees or 2 generalized degrees, but no, because it is very difficult to solve. Okay, let me proceed, and then I'll give you a specific example for instance L equal to, etc. And again, from here, when you have this expression, you can start marginalizing and understand how marginals from this joint distribution are related to the ordered parameters that then you are going to use for the calculation of the spectral density. But here my worry is to have a neat expression for the spectral density. Questions? Okay, so let me move for the spectral density. So it is the following. So given a connectivity matrix C, I'm going to assume that the connectivity matrix will indicate that connectivity matrix is symmetric and therefore the eigenvalues are real. So assuming that for a given connectivity matrix with size n, the eigenvalues are given by this list. So the spectral density or the mean spectral density is just given by this, calculating the usual density. And the idea is the following. So this problem can be very nicely recast into a problem of particles interacting on a graph. And this was done by Edwards and Jones in 1976. And I don't know whether you know how this thing is done. You have some idea. So let me do it because actually it's just very nice to read this. So what you do is simply realize that it's the following. So what you do is, so let me do it there. What you do is you have the spectral density. So let's forget about just the average over C over the ensemble. The spectral density is given by the sum for I from 1 to n of this delta lambda minus lambda I C. And what you do now is you look for a precision of the Dirac delta that is appropriate for the calculation, or where you want to go. In this case, what you do is a usual result from distribution theory that says the following, that 1 over x minus I epsilon, where epsilon goes in the limit epsilon going to 0 plus, is equal to the Cauchy principal value of 1 divided by x plus the imaginary unit times pi times the Dirac delta of x, right? And then the thing you have to do is simply realize that so you have a Dirac delta here, you have this result. So what you do here, this would be equal to limit epsilon going to 0 plus. Here is missing 1 over n, pi, take the imaginary part of the sum pi from 1 to n, 1 divided by lambda minus lambda I minus I epsilon. Yeah, and then you can write this thing as limit epsilon going to 0 plus 1 divided by pi imaginary part. Let's put that in here. Derivative with respect lambda, the imaginary part of the sum I from 1 to n of the logarithm of lambda minus lambda I minus I epsilon. Now the sum of the logarithm is the logarithm of the product. Logarithm of the product. And this actually can be written as the logarithm of the determinant of the matrix lambda minus I epsilon identity minus matrix A. Yeah, and the last step is like you can write the determinant of a matrix using a Gaussian integral representation, and then that's it. So at the end, what you have, if you have managed to recast the problem of calculating the spectral density for a given matrix into a problem of calculating the partition function, you allow me to say partition function. Of course, here you have imaginary units, etc. But let's assume that I can do the partition function of particles interacting on a graph. And since we are all physicists, we are now in familiar terrain, so we like to use the beautiful techniques, like for instance, these are disordered system, replicas, locality, or whatever you have. Clear? Very good. Let me just say a few words how this problem was studied previously. So there are quite a few works. Previous works, what they did, they used Replica method to tackle this problem. And at some point, they noticed that the side points they get they are very difficult to solve, and what they do is a series of approximative schemes. This was done by Biroli Monazon, Nagao Tanaka, Nagao Rogers, also Semergia, Curiandolo, etc. And so what we found out is like there is a way actually to solve at a certain level the Salton equations exactly without having to do any type of approximation. Right? And it's what we do in this example. I will tell you what is the approximation, what you have to do to solve this problem exactly. Actually. Questions about this mapping of a spectral density to a system of interacting particles? Okay, very good. So let's carry on. So here, what I do, I'm going back to actually to this partition function. Notice here that the spectral density is given by the logarithm of the partition function, which is, if you wish, the free energy. But you know, here I have a problem that I have to the average of the logarithm of the partition function, and the disorder is here. This connectivity matrix is here. So in order to do this average in a disorder system, we use a trick which is called replica method, which it works as follows. It tells you that the average over this ensemble of matrices of the logarithm of the partition function is equal to the limit of this index small n going to 0, 1 divided by n, the logarithm of the average of the n replicas of the partition function. And what we have to do is simply we have to take your system. You assume actually that this n is integer. So you take a system, you copy n times. You have, which is just taking the partition function to the power n. Then you do the average over the disorder. You do certain assumptions. You take the log, and then you take the limit small n going to 0. So again, so here in Delset we can discuss all the details.
Should be no log in the right hand side.
Here, yeah, this log. Yes. The usual. There are two ways. I don't know where this is coming from. There are two ways of writing this thing down. So one way is the limit of n going to 0 of 1 divided by n partition function n minus 1. This is one way, and the other way is that one. We can. It's just a couple of lines to notice that these two things are equivalent. No? In the end, what happens is the following: that in the limit n going to 0, so this should be 1 minus 1. So that's why you have this one here. By just my intuition, this is, you know, the partition function is going to be the exponential of something. You're going to use a steepest descent. So this is after doing a steepest descent. So you are going to have the logarithm of the exponential proportional to a small n, which is the number of replicas in capital N, which is the system size. So this limit is okay. Yeah?
I'm trying to understand the formula. I understand this one, but I don't see this one.
We can, sorry. So again, let me spell you the details of the calculation, but in this case what you do after doing the average of the disorder, so sites are coupled, so what you do is you decouple sites by coupling replicas because you want to go to a very nice expression where you can apply this steepest descent. So this is done by introducing this type of order parameter. Again, when I say order parameter, I mean in that way decoupling sites by coupling replicas. And at the end of the day, you have a very beautiful average replicated partition function, which is this one, with the usual integral over order parameters of the exponential, a functional times n. So it has the appropriate form to the steepest descent method. The functional has this horrible form. So again, so the limit n going to infinity, you want to apply steepest descent method. These are the cyclone equations. I don't want to scare you with this, but this is the usual type of equations people find previously. And in principle, it was thought that the type that one could find a simple way to solve them somehow. Okay, and the way to solve them well after doing replica-symmetric ansatz is the following: that is actually, and this intuition for me came from using Calculation method, which is much more intuitive than replicas, I must say. Is assuming that this order parameter is just a kind of a convolution or superposition of Gaussian distributions. And this actually is quite very intuitive, because if you go to to what the system is, so you are recasting the problem into of finding the spectral density into a problem of particles interacting in this way. So this just this is a Gaussian problem with Gaussian interaction. So what you would expect is that the superposition of Gaussians is going to appear as an order parameter, and this is what it happens. Okay. So, okay. So, again, I will show you the details, but I'm going to give you, if you're interested later on, you just plug this ansatz here, which is the replica symmetric ansatz. But here, assuming that this, what is called marginals, are Gaussian, and this, just for simplicity of the calculation, these densities here are normalized, and these are normalization factors, because in principle, these ordered parameters are not normalized. You put this thing into there. Questions? You put this thing into the cycle equations and also the expression for the functional, to the replica limit 0, etc. You massage the terms a bit, and again at the end of the next day, what you find is that this ordered parameter, which is this density that appears here, has the following cycle equation. So this density depends on this other density, which one? So this density depends on this density, and then there is a simple equation relating these two densities the other way around. Okay. Again, so what I'm not interested here is about this horrible formula, but is to realize that actually what it is in brackets, is precisely the expression for the conditional distribution that I calculated in the first case. So whatever horrible is this expression, it turns out that it has a very simple statistical meaning, which is this conditional distribution. So I can forget of trying to solve the order parameters here that are related with the statistics of the ensemble of graphs, and the other thing I can say is like whatever the parameters in the ensemble. So at the end of the day, okay, the joint distribution, well, this that appears in this expression for this order parameter is just this conditional distribution, and this is what just completely linear. Okay, so just plugging this thing into here. So when applying the fact that this is this conditional distribution, you have a very simple equation for these densities of these variances of the Gaussian distribution. And of course, okay, so this might be very interesting, but in the end of the day, I want to calculate the spectral density, and the question is how is the spectral density related with these densities? So spectral density is related with these densities as follows. So spectral density is just related with given another density, which I call here psi fixed for some reason of delta given k, and this density is given as a function of this previous densities that obey this equation. And that's it. So that's my solution. As simple as that. So, well, as simple as that. To a certain degree, right? So again, so let me do summarize. So I started trying to understand how to have an ensemble of graphs that have certain general degree correlations. Okay, to do so, I just introduced a model that you may like to know, and that model has a certain control parameters to achieve certain degree correlations, the ones you want. Right? So then I realized that well, the statistics of that ensemble can be more or less summarized or captured by a certain kind of joint distribution for the generalized degrees. So I don't care about the specific expression between this joint distribution and the other parameters, because I can circumvent that problem by saying, okay, so whichever parameters I choose, I have a given joint distribution for generalized degrees. So just you give it to me, I'll plug it in this formula. I solve this formula numerically. Sometimes you can do it exactly. And once I've solved this thing numerically exactly, I'm able to calculate the spectral density. Yeah. So I'm going to give now a couple of examples to see that, well, to have to clarify some ideas. Do you have some questions?
I mean, the only input in the spectral density will be decay, which is the degree.
Yes. Yes.
So
like
I
for
have
instance,
a scale-free network, so I put pdk over there, and I get the spectral density.
yeah, like for instance, no. Suppose that I consider the particular case of where my generalized degrees, I just take the degree correlation, for instance, and I take this capital L equal to 2, so I consider first generalized degree and second degree, for instance, or whatever. The point is that whatever you give me, okay, suppose that you want to calculate the spectral density of an ensemble of graphs that has a given joint distribution for joint distribution for 2 degrees k and k prime, and then the degree distribution. And the other thing you have to tell me is, like, in principle, you want to assure me that those graphs are tree-like stars and things like that. That's something you have to tell me. But if you give me this, yeah, I can put them in this system of equations. I can solve them numerically, sometimes exactly, and then from that I can calculate the spectral density. Yeah.
And in the case where you have triangles, so you have tree-like locally.
But this is the thing we discussed, this morning actually, in private. So you have to tell me what you mean when you have triangles. Okay, and it's also what I was discussing also with another person. Okay, because at the end of the day, what happens is, like, you can solve this type of problems because you have a graph which is tree-like, like this, and you can solve this type of problems. And actually, I must say that before going into that if you allow me to go back when I do the mapping to calculate the spectral density to having a system of interacting particles, it's like I solve this problem for a given complex network, right? But to solve this thing, it doesn't matter whether here I have an interacting particles with this type of interaction, or I could have a couple of oscillators. I could do also study dynamics, etc. So more or less the general idea is the same, and perhaps the techniques you are going to use to study dynamics are going to be different because they're going to be genetic differential analysis, etc. But the machinery is going to be the same. So the type of mathematical, hard work you are going to have to do is going to be essentially the same. Yeah? Now, going back to your previous question and trying to answer that, as we were discussing this morning, actually. So the general intuitive idea why you can solve this type of problems or graphs is the following. So the idea is that so essentially these graphs, sparse graphs, are locally tree-like, right? So what I mean by this is the following. What I mean is, like, if I look at a neighbor at a given node I, it has this type of tree-like shape. But not only that, the point is the following. If I look at the neighborhood of I, I suppose that there are some dynamical variables interacting, let's say Ising spins. Suppose I have here a spin sigma 1, spin sigma 2, sigma 3, and sigma 4. So then you can try to understand the following questions. What is the joint distribution for this spin? So what is the joint distribution that these spins, sigma 1, sigma 2, sigma 3, and sigma 4, have a given value? Okay? And the idea of these problems, why you can solve them easily, in principle, is the following. Suppose I do the Gedanken experiment of removing side I, right, from the graph. So I take this thing out, right? If, when doing so, these dynamical variables, they correlate, then I can solve the problem exactly. Exactly, again, to a certain, equations after of numerical stuff in that way, right? That means that essentially what I'm trying to say is that these dynamical variables sigma 1 to sigma 4, they fill each other. They are correlated mainly through I, the node I. If I take I out, they become uncorrelated, right? So here what I mean mathematically, if I calculate the joint distribution for these dynamical variables when side I, let me put it this way, has been removed, this would be equal to the product for L equal to 1 up to 4 of the marginals at each side for these dynamical variables sigma L, where side I has been removed. Right? In cases where this is exact, so that's very good news for you. In cases where this is not exact and you can use it as an approximation, this is called Bethe-Weiss approximation. Right? And the idea essentially is that all these problems can be solved again somehow to a certain degree, exactly. No Bethe ansatz, that's another ansatz in another field. Bethe-Weiss approximation. And the idea is, like, in this type of problems, so you can, try to you can solve things exactly to a certain degree because you have properties of this type. And notice that this property is relevant to the fact that you have a correlation between nodes I and J. What is important is that you don't have short loops. You are allowed to have long loops that behave like the loop of the system size or something similar. But if you have something like this and you have this property, then you can solve. You cannot always use this machinery, then you can have this exact results. Right? And now, to that particular case, when you are asking me what happens if you have triangles, you have to first of all tell me what you mean as having triangles, because I can understand many things. Like for instance, if by having triangles, what you mean is like I have
the neighbors, the fair neighbors are connected, basically.
Yeah, but suppose that I have a situation like this, no? I can have, triangles. Let me use another one, because this is fading away. Suppose I have, I can have, triangles of these guys, and these are connected to another triangle of guys, and this is connected to a triangle of guys, and this is connected to a triangle of guys, etc. Right? So now assume that we try to do the same and remove one guy. Like for instance, this guy here. This now is our I. So if you remove this guy, the neighborhood of I doesn't decorrelate. But the point is the following. If I remove the triangle, then the marginal for the triangle decorrelates with the marginal for the other triangles. So what you can do very easily is simply to generalize this case in case that you have communities, and the only thing you have to do is to take out communities, and the problem, this machinery will work as well as in the simple case. And again, everything is nice and many things. And actually, in the paper we also did a very simple case of communities, but I'm not going to explain it here because it's just a straightforward generalization of this technique and these ideas. Yeah. So let me actually go ahead.
Let me see if I understood correctly. I mean, with this mapping, what you're saying is that given a matrix, adjacency matrix, so that in values are giving you information about a system of interacting particles described at that Hamiltonian?
Yes, but again, yes, what I'm saying, I know where are you coming. No, it's just a mapping, right? What I'm saying is like, calculating the spectral density here, mathematically is equivalent of trying to understand and actually calculating the second momenta of a system of interacting particles following this Hamiltonian. This is what I'm saying, right? And again, so here you have to take this into a pitch of salt. For the following reason, here I have imaginary units, so this is not a partition function, this is not visible. A Hamiltonian, well, if I remove the imaginary units, you can understand as a Hamiltonian. But if you think about statistical mechanics, right? So the techniques we have to target, to try to calculate the marginals for the partition function. Doesn't really matter we have here a imaginary unit or you can put this in a partition function, right?
Yeah, I mean, the question is, if you try to calculate the spectral density of the Laplacian, this is giving you information about random growth on the network.
Yes.
So my question would be just follow the same mathematical approach. You will reach to some partition function when you really see that dynamics represented in there, or no? I mean, that's what I'm trying to say.
I would say no. I would say that this no, because this is just a system, your artificial system to understand the spectral density of the Laplacian in terms of particles interacting.
No? That's equally natural, right? That if you are calculating the Laplacian, at least you know that this is giving you information about the diffusion process there, you would expect that if mathematically this can be mapped to something that could have some practical interpretation, that would be the natural way.
Completely agree, but the point is like dynamics you can study it in any system, no?
Yeah. But then that changes, right? Because if you change the matrix, that changes that, and if you change...
Yes, but what I mean by that would, for instance, I could have any system of p-spins interacting. I can have a p-spin model, I can say dynamics on that, I can have models and things like that. Then, in order to understand dynamics, I want to study the Laplacian, etc. And trying to say is like, if you want to study the spectral density of the Laplacian, you can use a similar technique, and then you have to study the statistical properties of a system like this, where essentially here you have a different matrix.
Yeah, but that's precisely good, because if you try to see what is the relevant topological feature in order to explain some dynamics, and you don't know a priori, I mean, the case of the random walk is quite easy, but for other dynamics that could be very complicated. And you don't know what is the matrix, you have to, let's say, diagonalize or whatever, try to find a value. Just doing this mapping could help you to understand that. That was my guess.
Yeah, it does. Yeah. The question is also, so we have a future project, we can discuss later on with Conrad to study spectral density of Laplacian operator, but in the case where you have graphs which are generally directed, where the connectivity matrix is doesn't have to be symmetric. But we can discuss this. There are works by a colleague of mine from Pérez College where he has studied the Laplacian, the spectral density of the Laplacian operator. And there is other work as well. Actually, there is a work as I think there is a paper by Derrida and Gardner where they study the Laplacian, the spectral density of the Laplacian. And it's a paper from the 80s. We can try to dig it up later. More questions? Let me just give you another example. Okay, so. Well, let me actually. How long do I have? Well, so let me actually skip. There is a way to solve numerically this set of equations, which is called it's a technique that is called population dynamics. So I'm not going to explain that for just lack of time. But in principle, what we do is we solve this set of equations numerically, and then we, for a given graph ensemble, then we also take some graphs and we analyze them numerically and we compare results. And also to generate graphs, what we do, we use the Steger-Wormald algorithm, but we adapted so that we have a given degree distribution. This is very easy. This is very quickly. So going back to the previous question, so this is a trivial example. No? Suppose you give me a given degree distribution, which is this one, and a given conditional distribution, which is equivalent of giving just the joint distribution of having two degrees with a given connectivity, k and k prime. You give me this, and I can put them in the equations, solve them numerically using this population dynamics, and then I compare with a numerical diagonalization, and this is the result. Okay? The numerics are done very fast, very easily. Just I think in a matter of a couple of minutes you can have this thing. Of course, we do average over ensembles and things like that to have similar results. And this, perhaps I can explain later on why this picture has this form. You can understand this form in the following sense, because this conditional distribution is such that degrees of connectivity 2 tend to be with degrees of connectivity 2. The ones with of connectivity 3, degree 3, tend to be with not with connectivity degree 3, and the same with 4. And actually, this if you know what is the spectral density of a random regular graph of connectivity 2, 3, and 4. They look something like this. This is the one of connectivity 2, actually something like this, going up, down, up. And this is reminiscence of the one of spectral density of a random regular graph of connectivity 4. Right? But again, so you see, the main idea is the following. I forget about these functions, this Q, these parameters I was using at the beginning. You just give me, in this particular case, this the degree distribution and this conditional distribution, and then I give you the spectral density. Exactly. Right? And then in this next example, what I wanted to do here, we have to understand the following. Suppose that you have a given graph ensemble, but for some reason you are unable to see all the information. So what I mean by this is like you can reduce the knowledge you have for the graph ensemble to just, let us say, degree distribution and this conditional distribution. Okay? And then you would like to see how this lack of information, okay, is going to impact the spectral density if you have actually the exact description for the graph ensemble. And you see that actually changes a lot. And this example is very nice. This example is for n equal 2. And this example, it works as follows actually. So we allow to have only generalized degrees for the different nodes that are taken from this pool of 3 cases. And what this means is the following. So you can have, and I'll show you the picture and I'll finish with this. Right? And what you can have is the following. So you can have nodes of connectivity 2. Right? And then that's the first column. And then you can have nodes of connectivity 3. And then you can have nodes of connectivity 4. Yeah? And then the node of connectivity 2 must be such that it must be connected to 2 other nodes in such a way that the sum of neighbors for those nodes is 7. Right? So the other possibility here is like if I connect this guy to something, it would be a node of connectivity 3. Yeah, 1, 2, 3, and then a node with connectivity 4. Yeah? So a node of connectivity 2 would be connected to a node with connectivity 3 and another one with connectivity 4. And there, in this particular case, there is no other possibility, but we are choosing this example. It's that simple. So for the one of connectivity 3, so in this case, now the second generalized degree is such that it's 6. So that means that the number of neighbors for the neighbors of this guy must be such that the total number is 6. So that means that here the only possibility is I connect this guy to other nodes with connectivity with degree 2. 1, 2. Right? And I don't have any other possibility. And finally, for the nodes that will have connectivity, degree 4, so these nodes must be such that they are connected with nodes in such a way that the total sum of neighbors is 8. And the possibility is, so have here 2, 2, 2. Yes? Yeah, so what is the possibility? So the possibility is like if you have this graph, you have an ensemble like this, you have a very nice, perfectly regular graph with certain periodicity. No? Like for instance here you have this kind of broccoli type of picture. So you start with a node with a degree 3, and then you go to a node of degree 2, so degree 3, degree 2, and you go to degree 2, you can go to degree 4, and then from degree 4, degree 2, and so on and so forth. Yeah? So this, if in case you would have the exact information. But suppose for some reason you don't have the whole information, you try to capture somehow some of the statistical properties of this ensemble. So you can do a quick counting, and what you find is like the degree distribution is given by this formula, and then this marginal distribution is given by this formula. Yeah. And now, so let's assume I have this information. To me, if I only consider that I have this information for the ensemble of graphs, what I obtain is a picture like this, right? Where the graphs, the different nodes are uncorrelated. And if I consider certain correlation between the nodes given by this formula, then I have this intermediate picture. And the question is the following: okay, if I calculate the spectral density here, here, and here, how different they are? And it turns out that they are very, very different. So, okay, so I'm not going to go into the details. So for this example, you can do it exactly. You can actually calculate this exact formula for the spectral density. And it has this form, and we have checked this thing also using this, the analyzing numerical mathematics and things like that, so that we have the correct formula. And then if you just approximate the graph by just the minimal information you can have, which is just the degree distribution, you obtain a spectral density which is completely different, which is this one, not decimal whatsoever. And you try to incorporate a bit of information, like incorporating this marginal distribution, you would expect to capture a bit more. Yes, you do, but still it's pretty much different than the exact one. Okay, so I think I'm finished. So let me conclude. So what we have discussed here is just to wanted to calculate the spectral density somehow exactly for random graphs with constraint topologies, and the idea is that, sorry about the diagrams actually. So we wanted somehow to incorporate complex correlations in the usual approach that we could somehow mimic better in case of complex real-world complex networks. So it turns out that statistics for generalized degree have a significant impact on the spectral density. So if you miss a bit of information, the spectral can change a lot. And what would be interesting, I think going back to the question, is like how we could incorporate loops to the calculation, because again, if you think about the discussion I had before, so this calculation is based on the fact that I don't have short loops. So, but in real networks, complex networks, you in this code will have also loops. What do I have to do in this mathematical approach to incorporate those loops mathematically? And this is part of the feature work, and also to consider, non-remission. And that's
all the questions in the seminar, you want to ask any other questions?
And then what do you do with the spectral density?
that's
Publish it.
Which information do you, when you see this picture?
yes. So spectral density, knowing for instance, the eigenvalues of having general properties of eigenvalues of the given matrix is very important in many areas for some reasons. One reason is, for instance, analyzing a given graph is calculate the spectral density of the Laplacian. But let me put you a particular case. A particular case is coming as back as the 40s. It was a problem that was trying to be understood by von Neumann and other people, which is the following. Suppose that you have a linear problem, like for instance, a matrix A times X equal to B, and matrix is large, you want to try to solve this thing somehow iteratively, right? And then you would like to understand, this is a very particular example, you would like to understand whether this iteration to approach to the solution is going to be stable, instabilities are not going to grow, things like that. Okay? So it turns out that everything is reduced to try to understand, and this again can be in various ways, to try to understand the statistics of the so-called condition number. And the condition number, there's a very nice thesis by Edelman from MIT, which has a very nice thesis, very nicely to read. So the condition number, if I remember correctly, is the square root of the maximum eigenvalue divided by the minimum eigenvalue. Again, you have to take this thing with a pinch of salt. I'm just chit-chatting with you. What he's considering in this case, where what you do is what von Neumann perhaps did, that is multiply this thing, multiply this thing by the inverse, and then you have this one, the transpose, I think this is the transpose, and then you have, and then what you do is you invert this, the transpose of A times A, and then the eigenvalues are positive, and things like that, so there is a meaning for the minimum eigenvalue too. So, for instance, one possibility why this information is useful in this context, because of this.
What I mean in this one?
In this one, for instance,
which information do you get from the graph?
Well, that's okay. Let me go back to another problem. This was problem by Cass, or I don't know how to pronounce this properly. I think that was a problem by Cass, but I always mixing with another person. I think that he had a problem, a paper which is entitled "Can you hear the shape of a drum?" So that means I give you the frequencies when you beat a drum, you hear them. Can you understand the shape? I think that the answer is a very well-known mathematical problem. The answer is no. Now, if you're asking me if you show me a spectral density where I can tell you for which graph it's coming from, I would say no. Okay? And there's a very good reason for that. Well, at least intuitive reason. Of course, when I say no, again with a pinch of salt, because I can say no within boundaries, but there's a reason for that. Okay, what is the spectral density? Is just the diagonalized matrix. What is the diagonalized matrix? Is just take, so the determinant of matrix C minus lambda times the identity matrix. But if the eigenvalues of a matrix of this matrix are equal to the eigenvalues of any matrix which is similar to this matrix, that means S minus 1, right? So what can I say? No? So this can give some topological properties, this can give something else. I would say in principle, by looking at the spectral density, you cannot say much about the topological properties of a graph. For instance, I wouldn't be able to tell you whether there are communities. I don't think it's possible. Again, to a certain range of boundaries of the problem, right? Yeah.
Well, my question goes to the same a bit, but would you say at least if there's things repeating, like patterns repeating within the graph, or something like, you know, these motifs and metabolic networks, that they have motifs repeating, would you see that in the spectrum? Because, or what would you see?
I would say that my answer is no. You wouldn't be able. I mean, you would see something. The point is the following: you would see something, but you don't know where this is coming from, having just communicated.
Wow.
No? But that doesn't mean, again, that if in this paper again we study spectral properties of graphs and communities, where the fact of finding communities affects again the general shape of the spectral density. But you know, the shape can be affected by many things, so you don't know where those new features are coming from communities or not.
Other questions? Let us not speak it again. 7:30 will be a conference, a popular conference on the beauty, how men and women appreciate beauty in different ways. That will be in the Sarriera in Palma, 7:30. Given by Rick Munar, who collaborates with Cloud University.
No, pero sí, después de la teoría espectral, pues cuando los resultados matemáticos